Power lines do not favor cold temperatures. The lower the temperature, the greater the resistance within the power line. This elevated resistance can potentially trigger power outages. The underlying reason is that electrons encounter increased difficulty navigating the metal conductor when it is subjected to cold conditions. When examining the news report, the decision to defrost the underground power lines using a blowtorch was a measure to sustain the city's electrical grid functionality. The necessity for this action arose because the frigid weather had led to the freezing of the lines, impeding the current of electricity. In scenarios where temperatures drop substantially, the conductivity of power lines experiences a decline. This phenomenon occurs because the movement of electrons, which are responsible for carrying electrical current, becomes more hindered in colder environments. Metals, which are typical materials for power lines, possess a crystalline structure. In warmer conditions, electrons can traverse this structure relatively unhindered. However, as the temperature decreases, the atoms within the metal lattice vibrate less, reducing the space available for electrons to move freely. This diminished mobility results in increased resistance to the flow of electricity. The resistance in a conductor is the measure of its opposition to the flow of electric current. It is measured in ohms. According to Ohm's law, voltage equals current times resistance. For a given voltage, if the resistance increases, the current decreases. This reduction in current can lead to a drop in power delivered through the line. In extreme cold, the increased resistance can cause a significant drop in voltage and power, potentially leading to power outages. Utilities employ several strategies to mitigate the effects of cold weather on power lines. Firstly, burying power lines underground provides a degree of insulation from extreme temperature fluctuations. The ground temperature is typically more stable than the air temperature, which helps to keep the lines warmer in the winter. Secondly, insulation materials can be applied to overhead power lines to reduce heat loss and prevent freezing. These insulation materials act as a barrier, slowing down the rate at which heat dissipates from the lines into the surrounding environment. Thirdly, increasing the current flowing through the lines can also help to keep them warm. This strategy is based on the principle that the heat generated in a conductor is proportional to the square of the current flowing through it. By increasing the current, the power lines can generate more heat, which can help to offset the effects of the cold. Another factor contributing to the issues with power lines in cold weather is the potential for ice accumulation. Ice buildup can significantly increase the weight of the lines, potentially causing them to sag or even break. Furthermore, ice can act as an insulator, further reducing the line's ability to dissipate heat. The use of a blowtorch, as mentioned in the news report, is an extreme measure typically reserved for emergency situations. It is a temporary solution to thaw frozen lines and restore power quickly. However, it is not a long-term solution, as it can damage the lines if not done carefully. A more proactive approach is to implement regular maintenance and inspections of power lines, particularly in regions prone to extreme cold weather. This includes identifying and addressing any potential weaknesses in the lines, such as corrosion or damaged insulation. Also, predictive modeling can be used to forecast the impact of cold weather on power grid performance. This involves analyzing historical weather data and power grid performance data to identify potential vulnerabilities and develop strategies to mitigate their impact. Power companies also have emergency response plans in place to address power outages caused by cold weather. These plans typically involve deploying crews to repair damaged lines and restore power as quickly as possible. Power grids are complex systems, and their performance is affected by a variety of factors, including temperature, humidity, wind speed, and precipitation. Power lines can be made of different materials such as copper or aluminum. Copper is an excellent conductor of electricity, offering low resistance to the flow of current. It is also relatively resistant to corrosion, which is important for outdoor applications. Aluminum is another common material for power lines. It is lighter than copper, which can be an advantage for long-distance transmission lines. However, aluminum has a higher resistance than copper, so larger conductors are needed to carry the same amount of current. The size of the power lines also plays a role in their performance in cold weather. Larger conductors have a lower resistance, which means that they can carry more current without overheating. However, larger conductors are also more expensive and heavier. The voltage of the power lines is another important factor. Higher voltage lines can transmit power over longer distances with less loss. However, higher voltage lines also require more insulation and safety precautions. The design of the power grid also affects its performance in cold weather. A well-designed grid will have multiple pathways for power to flow, so that if one line fails, power can still be delivered to customers through alternative routes. Also, the grid should be designed to withstand extreme weather events, such as ice storms and blizzards. The National Electrical Code, or NEC, provides guidelines for the safe installation and maintenance of electrical systems, including power lines. The NEC addresses issues such as conductor sizing, insulation requirements, and grounding. Compliance with the NEC helps to ensure that power lines are installed and maintained in a safe and reliable manner. One aspect to consider is the type of insulation used on the power lines. Different types of insulation have different temperature ratings. It's important to use insulation that is rated for the lowest expected temperature in the region. This helps to prevent the insulation from cracking or becoming brittle in cold weather. The depth at which underground power lines are buried is also important. Burying the lines deeper can help to protect them from freezing. However, burying the lines too deep can make them more difficult to access for maintenance and repairs. The use of heat tracing systems can also help to prevent underground power lines from freezing. Heat tracing systems involve running a heating element along the length of the power line. This element generates heat, which keeps the line warm enough to prevent freezing. Another technique used to prevent ice buildup on overhead power lines is to apply a special coating to the lines. This coating prevents ice from adhering to the lines, reducing the risk of sagging or breaking. The angle of the power lines can also affect their susceptibility to ice buildup. Lines that are angled downwards are more likely to accumulate ice than lines that are horizontal. Power companies sometimes use drones to inspect power lines in cold weather. Drones can access areas that are difficult or dangerous for humans to reach, allowing for more thorough inspection of the lines. Infrared cameras can be used to detect hotspots on power lines. Hotspots can indicate a problem with the line, such as a loose connection or damaged insulation. Early detection of hotspots can help to prevent power outages. Power companies also use weather forecasting data to predict the impact of cold weather on power grid performance. This data can be used to adjust the grid's operating parameters to minimize the risk of power outages. In some cases, power companies may need to shed load to prevent a widespread blackout. Load shedding involves temporarily disconnecting power to certain customers to reduce the overall demand on the grid. Power companies typically prioritize critical infrastructure, such as hospitals and emergency services, when implementing load shedding. The use of smart grid technologies can also improve the reliability of power grids in cold weather. Smart grids use sensors and communication networks to monitor the performance of the grid in real time. This allows for faster detection and response to problems. Smart grids can also be used to optimize the flow of power through the grid, reducing the risk of overloads and voltage drops. Batteries can also be used to provide backup power in the event of a power outage. Batteries can be installed at homes, businesses, and substations. They can provide power for a limited time, giving power companies time to repair damaged lines and restore power. Distributed generation resources, such as solar panels and wind turbines, can also improve the reliability of power grids in cold weather. These resources can provide power locally, reducing the strain on the main grid. Power line icing is also a critical consideration. Ice accumulation on power lines can lead to several problems. Firstly, the added weight of the ice can cause the lines to sag excessively, potentially leading to contact with trees or other objects. Secondly, the ice can cause the lines to vibrate in the wind, which can lead to fatigue and eventual failure. Thirdly, the ice can act as an insulator, preventing the lines from dissipating heat and increasing the risk of overheating. The icing techniques are used to remove ice from power lines. One common technique is to use helicopters equipped with specialized icing equipment. The helicopters fly along the power lines, spraying them with a de-icing fluid that melts the ice. Another technique is to use ground-based de-icing equipment, such as trucks with telescoping booms. The trucks can be used to reach the power lines and spray them with de-icing fluid. In some cases, power companies may use controlled blackouts to remove ice from power lines. A controlled blackout involves temporarily disconnecting power to a section of the grid. The sudden change in current can cause the ice to melt and fall off the lines. This technique is typically used as a last resort, as it can cause inconvenience to customers. Regulations and standards play a crucial role in ensuring the reliability of power grids in cold weather. Regulatory agencies such as the Federal Energy Regulatory Commission (FERC) set standards for power grid operation and maintenance. These standards help to ensure that power companies are taking the necessary steps to protect their grids from the effects of cold weather. Professional organizations such as the Institute of Electrical and Electronics Engineers, or IEE, also develop standards for power grid design and operation. These standards provide guidance on best practices for designing and operating power grids in cold weather environments. It is critical to consider the impact of climate change on power grid reliability. Climate change is leading to more extreme weather events, including more frequent and intense cold snaps. This increases the risk of power outages caused by cold weather. Power companies need to take climate change into account when planning for the future. This includes investing in infrastructure that is more resilient to extreme weather events. It also includes developing strategies to adapt to the changing climate. The aging infrastructure in many power grids also poses a challenge. Much of the existing power grid infrastructure in the United States is decades old. This infrastructure is more susceptible to failure in cold weather. Power companies need to invest in upgrading their infrastructure to improve its reliability. This includes replacing old power lines, substations, and other equipment. Public awareness is also important. The public needs to be aware of the risks of power outages in cold weather. They also need to know how to prepare for a power outage. This includes having a backup plan, such as a generator or battery backup system. It also includes knowing how to stay safe during a power outage. Power companies can help to raise public awareness by providing information on their websites and through public service announcements. Collaboration is key to ensuring the reliability of power grids in cold weather. Power companies, regulatory agencies, and professional organizations need to work together to develop and implement strategies to protect power grids from the effects of cold weather. This includes sharing information, coordinating resources, and developing joint plans. The increased use of renewable energy sources, such as solar and wind power, also presents new challenges for power grid operation in cold weather. The output of these resources can vary depending on the weather conditions. This can make it more difficult to balance supply and demand on the grid. Power companies need to develop strategies to integrate renewable energy sources into the grid in a reliable manner. This includes using energy storage technologies, such as batteries, to smooth out the variability of renewable energy output. The cost of upgrading and maintaining power grids in cold weather can be substantial. Power companies need to carefully consider the costs and benefits of different strategies. They also need to work with regulatory agencies to ensure that they can recover the costs of these investments. In conclusion, power lines are susceptible to the effects of cold weather. Low temperatures increase resistance, potentially leading to power outages. To mitigate these effects, utilities use various strategies, including burying lines, insulating them, and increasing current flow. Proactive maintenance, inspections, and weather forecasting play a vital role in ensuring power grid reliability in cold climates.